Hey, so I'm going to send you my notes in picture format too, but I'm going to do this video real quick because it might make a little bit more sense than my notes, because I don't take notes in a binder, I take it on the paper. And so I just wanted to send this video to might make a little bit more sense. So what we did today was we basically took all the information that we learned so far and a little bit more, and learned how to make a molecular structure given some data and all that. And so the first thing that you want to do is read the problem. And one of the examples today says that using an hnmr spectrum to determine structure of an unknown compound X that has a molecular formula C4H8O2 and contains a C double bond O absorption in its spectra. So how you attack these different problems is a step. He explained it to us. Is like a stepwise thing. So the first thing that you've got to do is calculate degrees of unsaturation. And excuse my handwriting, I'm not the best writer, but you probably remember how to do that from Organic 1. But just a quick short reminder. So our molecular formula was C4H8O2. And so the first thing we want to do when we calculate degrees of unsaturation is find the maximum amount of hydrogens possible. And that's found by the equation 2n plus 2. And n represents the number of carbons that we have. So in this one, it would be 2 times 4 plus 2, which is equal to 8 plus 2 is 10. So we have a maximum amount of 10 hydrogens from this compound. And so we actually have 8. And so to find the degree of unsaturation, all we do is the theoretical, basically, minus the actual amount of hydrogens that we have, divided by 2. So 10 minus 8 is 2. 2 divided by 2 equals 1. So we have 1 degree of unsaturation, and that means somewhere in our molecule we have a double bond. The second thing that we do is we look at our IR data. And if you look in the problem, this is on page 15, it says that the IR spectra that's given, it says that it contains a C double bond O. And so we know that, well, the same thing is we use IR data. And so we know that somewhere in our molecule, there's a C double bond O in it. So that's a useful piece of information. Well, if we look back at our molecular formula that they've given us, we know that there are 2 oxygens in it. And anytime that you have 2 oxygens, you've got 3 options. You can either have a carboxylic acid, which is a C double bond O, OH, or you can have an ester, which is a C double bond O, OR. And you could also have like a ketone and an hydroxyl somewhere else in there, but as he explained it to us today, that's not likely to do that. It's more straightforward. So really your 2 main options are either a carboxylic acid or excuse me, an ester in the molecule. And so knowing that bit of information, we go to the third step. And the third step is where we use our hnmr spectra. And so again, on page 15, we look at the different peaks that they give us. So we see at 1 ppm, we have a signal that integrates to 3. And so anytime you have a signal that integrates to 3, we know that that is a CH3. And then it also gives us the splitting pattern. And I know it's kind of small, but if you follow along with your notes, you'll be able to see it. It gives us the splitting pattern. It's 1, 2, 3. So this CH3 that integrated to 3 is split into 3 peaks, meaning that it has to be attached to a CH2, because CH2 is what would split this CH3 into a triplet. And so we go further to the second peak, and we see that there is a point that integrates to 2. So at 2 ppm, we have a molecule that integrates to 2H, and that's indicative of a CH2. And again, this splitting right here, it gives us 4 peaks. And so with those 4 peaks, we know that its neighbor has to be a CH3, because that's how you get a quartet. And so these right here, this data right here is just confirming what we already estimated or guessed to be right here. So we know somewhere in this molecule we have an ethyl group, CH2, CH3, somewhere in this molecule. And so the last peak in it, we see there's approximately, we'll say 3.6 ppm. So at approximately 3.6 ppm, we have a singlet right there. It's not split into anything. That's integrated to 3. So it integrates to 3. And so that means we have another CH3, and this CH3 is a singlet, meaning that there's no hydrogens that are by it that splits it. And so with that piece of information, we can now begin to piece together what we have. So we know that we have either an ester or a carboxylic acid, and we know that we have an ethyl group, and we know that we have a methyl group. And so there, now we look at the chemical shift of the data that's given, and on here it's 0 to 8. Well, that right there lets us know that we don't have the carboxylic acid, because this electronegative atom is going to pull this hydrogen right here. It's going to move it upfield to the left, because this is electronegative and all that other stuff that we went over. So we know that we don't have that. So now we know that at some point in our molecule we have the ester. So I'm going to draw that. So now we've got to decide, okay, does the methyl go here or does the ethyl go here? And I'm going to redraw this right here. So does the ethyl go by the oxygen or the methyl go by the oxygen? And we determined earlier that this methyl right here does not get split by anything. There's no neighboring hydrogens that can split that. And so that right there is indicative of letting us know that this has to be the group that's next to it, because if you see, there's no hydrogens around there to split this atom, and that will be indicative. And the chemical, on top of that, the chemical shift is further away than every of the other one, all of the other ones, because this oxygen is electronegative. And so that lets us know there. And so all that we have left to have is that CH2, that ethyl group that we had. And there you have it. That's our that is our structure, and that is how you do it. Just let me know if you have any questions. Okay.